Hello, wonderful algebra students, and welcome to your lesson video on equations and relationships. This lesson is really here to help us prepare for our last two lessons of this unit. So the focus of this lesson is going to be on exploring and just refreshing our memory about this relationship between equations and graphs. So there's going to be three different tasks we look at in this lesson. It'll be a good reminder of some of the things you might have learned in pre-algebra about graphs and equations, and it'll be essential stuff that we want to make sure we know going into tomorrow's lesson. The warm-up for this lesson is one of these activities. We've done these before, which one doesn't belong. So there are 4 linear relationships down here, and your goal is to pick one and make an argument for why it doesn't belong with the others. If you remember from when we've done these in the past, there is no one correct answer, so you could choose any of these 4. The focus is really on, can you make that argument and explain why it's different from the others? So you could say something like, well, this one here is the only one that doesn't have this, or this graph here is the only graph that does have this. It's all about that argument and convincing us why. So I'm going to go ahead and encourage you, pause the video now. Make sure you pause it, try this on your own, and then come back and see where you're at with some of the things we say. Go ahead and try that now. Okay. As promised, we said there's no correct answer for these, so you could pick any one you wanted and make the argument it doesn't belong with the others. I think a very popular one, for maybe obvious reasons, is picking this one here and explaining why it doesn't go with the others. You know, on first glance, it's very easy to say this is the only equation, the other 3 are graphs. But the focus of this activity as well is to bring in some vocabulary. And so if when you paused this video and did it yourself, you weren't using these words, see if you could go back and use one of these vocab words in your answer. We've got slope and Y-intercept. So one reason why C doesn't belong with the others is because it's an equation. But when I look at that equation, I know this number that goes with X is our slope, and this number is our Y-intercept. Y-intercepts are where the graph crosses that y-axis. So for example, Y-intercept, Y-intercept, Y-intercept. This Y-intercept is negative 7.5. So you might have argued C doesn't belong with the others because it is the only negative Y-intercept. And we can go through the others and make arguments, but a lot of those arguments are going to be using those vocabulary words, slope and Y-intercept. So going through the other 3, you might have chosen graph A, and graph A doesn't belong with the others. The reason is because of the slope. If I'm looking at the slope of this line here, if the line is going up from left to right, that means it has a positive slope. And none of my other graphs are going up. And if I look at my equation, the slope here is negative 2.5. So this is our only graph with a positive slope. That could have been your reason for this first one. Graph B, if I look at it, the word we use sometimes for that line is it is a horizontal line. If you've got a horizontal line, horizontal lines aren't going up, they're not going down. That means that that slope, which is the direction of the line, if it's not going up, it's not a positive slope. If it's not going down, it's not a negative slope. This graph here is the only graph that has a slope of 0. All the other ones have a negative or a positive slope. So that could be your argument there. And then that last one, D, you might have argued that D doesn't belong with the others because we've been talking about slope. The slope of this first line is positive. The slope of the second line is 0. The slope of this line is negative 2.5. The slope of this line is also negative because it's going down. So I can't say it's the only line that has a negative slope because we've got a negative slope here, but I could say it's the only line that's got a negative slope and a positive y-intercept because this one here is negative. You can get a little creative with your reasonings. But the really big goal from this first activity is just to practice using these vocabulary words of slope and y-intercept. So hopefully you recall, or it sounds familiar from pre-algebra, that slope is that direction of the line. It's telling you is the line going up, down, horizontal, vertical, and then your y-intercept is going to be where that line is crossing your y-axis. We are definitely going to be using these words again later on in this lesson. Speaking of later on in this lesson, I'm going to jump us to that next part, which is going to be this activity here. We are looking at more graphs because remember our goal for today is this connection between the equations and the graphs and what they tell us about the situation. So we've got 4 graphs here of linear equations, graph A, graph B, graph C, graph D. And our goal is going to be to use these 4 graphs to answer a couple questions. So we will start off with just number 1. Number 1 down here at the bottom is which graphs have a slope of 3? As I read through that, I notice the question says graphs, which means there's going to be more than one. When we're talking about slope and finding slope, that formula we used a lot was rise over run. So hopefully that jogs your memory a little bit. Just like we did earlier, pause the video. Getting practice for yourself is the best way to help this stick in your brain. So pause the video and see, looking at these 4 graphs, if you can figure out which graphs have a slope of 3. Go ahead, do that now. Okay. So we had said when we were talking about slope and graphs, we use this idea of rise over run. On a quick glance, I noticed we're talking about a positive slope. It's positive 3, which we had mentioned earlier. Positive slopes means our lines are going up. So I might use that to see if I could eliminate anything. But when I look at all 4 of these graphs, all of the lines from left to right are going up. So it doesn't help me eliminate anything. So I'm actually going to have to calculate slope. To do this, I'm going to make our graphs a little bit bigger for us. And to use that rise over run to find slope, I'm going to need 2 points on my line. When I'm picking points on my line, there are tons and tons and tons of points on this line, but I want to pick points that are intersecting with those graph lines. So for example, this point right here could be a good point to use because it's going through those graph lines. As I look through this line, there are lots and lots of points. I'm just going to pick the next one I see, which is right here. Coincidentally, it's our y-intercept. It doesn't have to be the y-intercept, but I'm going to use those 2 points. Rise over run means that I want to count how much I have to go up, that's your rise, and how much I have to go over, that's your run, to get from one point to the next. So I'm going to start at that first point I wrote. That's this point here, and count how many boxes I have to go up. That's 1, 2, 3 boxes. And then how many boxes I have to go over to get to the second point. That's 1 box. So notice I'm starting from that first pink point. I'm not starting down here at the origin or at my x-axis. Starting here at my first point, and I went up 3 boxes and over 1 box. 3 over 1 is the same thing as 3 divided by 1, which is 3. So I notice that this graph right here has a slope of 3. There's a very strong chance you did not pick the same points I did. You could choose any 2 points. So maybe you chose this point down here and this point here instead. Would we get the same slope or a different slope? What do you think? Well, the best way to find out is to do it. I'm going to start at my first point here and count how many up and over I need to go to get to the second point. So I'm going to count 1, 2, 3, 4, 5, 6. It's looking different. The rise is 6. The run is 1, 2. I'm getting a different rise over run, but when we do that division, 6 divided by 2 gives me that same slope of 3. This all goes back to that idea of what slope is. Slope is the direction of the line, and no matter what points I pick on this line, they're all going the same direction, right? My line isn't changing directions. It's going that same direction the whole time. So you can pick any points and you'll get the same slope. If we do that same thing for some of the other graphs, we can figure out which lines do have a slope of 3 and which lines don't. So if I come over here to graph B, if you weren't able to do this earlier, pause the video and see if you can find out what the slope of graph B is. Just like we said earlier, you can pick any 2 points. So maybe I choose this point and this point. I'm going to get the same thing we got earlier. I'm going up 3 and over 1, rise over run, gives me a slope of 3. Now, if we zoom out a little bit and look at those 2 lines together, what do you notice about these 2 lines? What do they have in common? I see the number 3, right? They both have a slope of 3, but just looking at the picture, do you notice what they have in common? I notice they're going the same direction. You know, if I compare the direction of this line and the direction of this line, they're both going the same, well, for you, it's this way. They're both going the same way on the graph. You know, this one's starting a little higher, this one's a little lower, but they're the same direction. Slope is direction. So if they both are going the same direction on the graph, we can conclude they have the same slope, which we're seeing right here. Now, if I peek down here at these other 2, notice those are going different directions. Those are different directions than these first ones. So just by knowing that slope is the direction of the line, I don't even need to stop and find rise over run of these. I know it's not going to be the same as this one because I see a slope of 3 looks like this. It's higher, and these ones down here aren't as high. I'm going to jump down to that second question. So to answer this first one, which graphs have a slope of 3, we figured out that graphs A and B have a slope of 3. That other question, number 2, I'm going to zoom out a little bit. Number 2 is which graphs have a slope of 1/2? Let me back up a little more. Now you can see them all. Just like we did earlier, pause the video. Give yourself that practice. That's going to make you a strong math student. Pause the video and see if you can figure out which graphs have a slope of 1/2. Okay. I hope that no one put graph A or B down. We already know the slope of graph A and B. The slope is 3, so I'm not going to say A or B have a slope of 1/2. I could come down to graph C and D and check that slope there. So I'm going to zoom back in, keep zooming in and out and in and out. Graph C, I'm going to do it the same way I did earlier. I need to find 2 points. So I'm looking through my line and looking for points that intersect with the graph. I see this one. Doesn't matter if you and I are picking the same point. So I'm going to choose this one, and I'm going to choose this one. And then I'm going to count my rise over run. It always starts with rise. Rise is always going to be on the top. Your rise is how many boxes you have to go up or down. So starting at my first point, I have to go up 2 boxes. And then my run is how many boxes I have to count over. So I have to go over 1, 2, 3, 4. So I get 2 over 4. Now my question is asking which graph has a slope of 1/2. What do you think about graph C? Yes or no? Well, I got the fraction 2/4, and that's not 1/2, but we know how to simplify fractions. Simplifying doesn't change the amount, it just makes the number smaller. So if I'm looking at 2/4, I notice I can simplify that fraction because there's a number we can divide both of those by. The number is 2. When I do that, 2 divided by 2 is 1, 4 divided by 2 is 2, and so we see that slope is 1/2. So I know graph C has a slope of 1/2. What do you think about graph D? Well, similar to what we said earlier, just looking at those two lines, I'm noticing they're going the same direction, right? They're in different places. What am I doing? Yours look like this. Okay. I have to, this is mirrored, so I have to go the opposite way. So I'm noticing those graphs, those lines are going the same direction. They're in different spots on the graph, but they're still going the same direction. So on first glance, I think they have the same slope. I could always check by picking 2 points and saying, yep, it goes up 1 over 2, up 1 over 2. So both of those graphs have a slope of 1/2. Now there are 2 more questions here, so I'm going to back out again. Number 3 is which graphs have a y-intercept of -1? So we are looking for a y-intercept of -1. I'm writing it up there so I can scroll up a little bit so you can see all the graphs. Just like earlier, pause the video and see if you can figure out which of these graphs are graphs that have a y-intercept of -1. So, trying to clean this up while you were figuring that out. Looking at our 4 graphs, we know y-intercepts are the points where these graphs cross our y-axis. And I see our y-axis is right here. It's that vertical line going up and down. On this graph here, I'm seeing it's crossing above our origin. It's crossing above 0. So that right away tells me it's not going to be a -1. Over here, I see it's crossing below 0. It is crossing right there at -1. So graph B would be an answer. The other one is going to be graph C. Graph C is also crossing right there at -1. So my answer for number 3 would be graphs B and C. The last one, number 4, says which graphs have an x-intercept of -2? Just like I did earlier, I'm going to come up here and write x-intercept of -2? Yes. Just so you can see all the graphs at once on your screen. And one last time, pause the video and see if you can figure out which graphs have an x-intercept of -2. Okay. The last part of this is going to be looking at our x-axis. I'll do this part in yellow. So if I'm looking at our x-axis, our x-intercepts are going to be where that line crosses our x-axis. For graph A, that number is -2. Graph B, I can't tell what number that is because it's in the middle of the box. It might be 1/2, it might be 0.4, 0.62, right? But I know it's not going to be a -2, so it's not graph B. Graph C is a +2. +2 and -2 are different things. Those are different sides of our graph, right? So it's not graph C. Graph D is also -2. So it's going to end up being graph A and graph D. Both of those have an x-intercept of -2. So I'm just going to write graph A and graph D. The purpose of this activity here was to practice, again, using that vocabulary, x-intercept, y-intercept, slope, and also to practice identifying those from a graph, especially slope, right? It's a good reminder of that rise over run formula we had. Now, there's still more questions using these graphs here. So if I jump down to number 5, in number 5, they tell us graph A represents the equation 2y minus 6x equals 12. So if I'm looking at graph A up here, they're giving me the equation for that line. The question is, which other equations could graph A represent? This is one way the equation could look, but there are other ways that equation could look. And we're given 6 options here. There's a couple ways we could approach this problem, but the theme of this problem is it goes back to that idea of equivalent equations. Remember that word equivalent means things that might look different, but represent the same thing. Earlier, I was talking about simplifying fractions. 1/2 and 2/4 are equivalent fractions. Numbers look different, but they're the same fraction. Here, we're looking for which of these equations below are equivalent to 2y minus 6x equals 12. We've talked about equivalent equations in a past lesson. If that does not sound familiar, go back and watch the video for equivalent equations. But what I would like you to do is go ahead, pause this video, and see if you can identify which of these 6 equations below could also represent graph A, given the fact that this equation here represents graph A. To answer this question, you don't even need the graph. We just need this equation here to help us figure out which ones are equivalent. I'm going to go ahead and encourage you to pause the video now, try that out. There's multiple correct answers, so make sure you check all 6 and come back when you're ready to see which ones are equivalent. Okay. So when we talk about equivalent equations, in that past lesson, we had talked about, let's move my face. We had talked about acceptable moves you can do to get from one equation to another. So for example, I'm allowed to add the number 2 to both sides of an equation, but I'm not allowed to add the number 2 to only one side and not the other. That wouldn't be acceptable. So our goal for this right here is, I could grab my graph paper and graph every single one of these lines to see if it matches up with that graph A. But we can use the knowledge we have about equivalent equations to see what move would I have to do to this equation to get this first one here. And then once we figure that out, we can decide, am I allowed to do that or not? So for example, if I'm starting with 2y minus 6x equals 12, and I'm comparing it to equation A, y minus 3x equals 6, can you figure out what math did I do to this first equation to get this? What I'm noticing is, especially looking at that 12 and 6, I notice this division here. I am dividing that side of the equation by 2 and this side of the equation by 2. 2y divided by 2 gives me y. 6x divided by 2 gives me 3x, and 12 divided by 2 gives me 6. Am I allowed to do that? Am I allowed to divide both sides of my equation by 2? Absolutely. So that lets me know equation A would have the same graph as the equation 2y minus 6x equals 12. I can also use the fact that this equation is equivalent to help me figure out some future equations. So when we come down to equation B, which is y equals 3x plus 6, I notice it looks similar to equation A. So I might see, can I change equation A to look like equation B? The difference here I notice is that minus 3x has just changed sides. If I wanted to bring my 3x over to the other side, I'd have to do the opposite of subtraction, which is addition. And that would give me y equals 3x plus 6, or 6 plus 3x, which is that equation we're looking at. What about equation C? What do you think? Well, the only difference between equation B and equation C is the sign on that 3x there. Up here it's positive, here it's negative. Am I allowed to come in and just put a negative sign wherever I want? No, of course not. That's like multiplying one part of your equation by a -1, but not the other parts. Remember, we've had this theme, right? Whatever you do on one side of your equation, you have to do on your other. So if I'm comparing equation C to the original equation, equation A or equation B, equation C is not equivalent. I'm not allowed to just throw in a random negative sign on one of my terms. So that equation would look different than our equations here. If I erase my squiggle for a second, we can talk about exactly what's different. What does that number right there represent on our graph? Well, if I come back to very early on in this lesson, we said that number in front of x represents your slope. So here, we can also think of this question like, does this equation with a slope of 3 and this equation with a slope of -3 look the same? And no. A positive slope would be a line going up, which Yes, a line going up, and a negative slope would be a line going down. I'll put that squiggle back over, saying that one is not equivalent to the others. Coming over here to equation D, what do we think about that one? Would that be the same as our other ones here? If you didn't do this earlier, go ahead and pause and see if you can figure that one out. As I'm looking at this one, I notice it looks similar to this one, so I might start there and see, can I change this equation to look like this? Well, I notice kind of like with equation B here, the x has just changed sides. If I wanted to move my 6x over to the other side, I have to do the opposite. I have to add 6x on both sides. That would give me 2y equals 6x plus 12, which isn't what I'm seeing here. I'm seeing a negative 6x plus 12. What do we think? Are these equivalent then? No, but this equation we just wrote would be, but not this one. Go ahead, try those last two if you have not already. So for those last two, for equation E, if I compare it and our original equation we have, what I notice is to go from here to here, we're multiplying by 2. 2y times 2 is 4y. 6x times 2 is, oopsies, the equation does have an x there, 12x. But whatever you do on one side, you got to do on the other. So only one of these are equivalent to that original equation, and that is going to be this last one here. If I'm multiplying that left side by 2, I would also have to multiply my right side by 2, which means that would need to be a 24, like we see in equation F. So out of all of these, 3 equations are equivalent, which would mean 3 of these equations would have a identical graph to graph A, which looks like this up here. There's one last thing I want to look at in this lesson, and that's going to be more about slope and intercepts. We've been talking about how to identify slope and intercepts from a graph. What I want to spend these last couple minutes of this video talking about is when we're looking at situations, because you know we look at a lot of situations in this class and the graphs of those situations, is what does the slope and the intercept tell you about the situation? So for this last part here, we're going to look at these different graphs of these situations described above, identify the slope and the y-intercept, and then talk about what those mean in terms of the situation. So for example, we can do this first one together. Number 1, we've got the printing company keeps an inventory of the number of cases of paper it has in stock. And then we've got this graph right here. As I'm looking at this graph and trying to make sense of it, one of the first things I like to do is I like to go and look at the labels. So I'm noticing my y-axis is talking about the cases of paper stock. So that's how many cases or like boxes of paper the printing company has. And then my x-axis is talking about the number of orders. I'm noticing the line goes down. Noticing the direction of the line is also helpful. And to me, it makes sense the line's going down because as we order more cases of paper, they're going to have less cases in stock, right? They're hopefully selling all of them, so they're going to have less and less. Our goal here is to identify our slope and our y-intercept and talk about what it means in the story. Let's start with that y-intercept. Looking at this graph, what is that y-intercept going to be? That y-intercept is that point on our y-axis, so that's going to be the number 60. In this story, what does 60 represent? 60 what? See if you can describe it as fully as possible. Well, I know if I'm looking at my label that 60 is how many cases of paper they have in stock. So I could say 60 is the cases of paper they have in stock. But there's a little more to it because remember a point has a pair of numbers. That 60 is the y-intercept. What is that x-intercept? not X-intercept, I'm sorry. What is that X coordinate? It's the number 0. That Y-intercept right there tells me that they have 60 cases of paper in stock if they don't sell any orders, meaning that's like the original amount they had. That's the starting amount of cases of paper they had in stock before they sold anything. That's what our Y-intercept in this situation means. Now, the other part of this is our slope. Slope with graphs. That goes back to what we had done at the beginning, right? With rise over run. So as I'm looking at this graph of this line, I want to find a point that intersects the graph lines perfectly. So you see right here how it's like really close, but not exact. I can't pick that point because I would have to make a guess at where it actually is, right? But if I go a little further, I can see there's a point right here. I want to calculate my rise over run. So starting here, I want to figure out how much I have to go up or down. That's going to be our rise. And then our run is how much you're going sideways. If I'm starting here, it might be tempting to say $1, $2, $3, $4. So our rise is 4. But look at our y-axis. We're not counting by ones anymore. I'm counting by larger numbers. If I go from a 60 down to a 40, how much did I decrease? Well, if I went from a 60 to a 40, 60 minus 20 is 40. So that rise, I need a 20 just because of the way our y-axis is numbered. But because I'm going down, I also need a negative sign there. I went down 20. And then our run, I went over 1, 2, 3, 4, 5. If I take a peek down here, we are counting by 1, right? 1, 2, 3, 4, 5. So my run is 5. Negative 20 divided by 5 is negative 4. So my slope is negative 4. But remember that extra step here. What does negative 4 mean? It can help here by thinking about that negative 20 over 5 first. What was negative 20 over 5? Well, negative 20 was, we said we went down 20 cases of paper. 5 was 5 orders. So we lost 20 cases of paper after 5 orders. When we do that division, if we lose 20 cases of paper after 5 orders, that slope is telling me we're losing 4 cases of paper after 1 order. That negative 4 means that they're selling 4 cases of paper per order. And I'm going to write that down. We are losing or selling, I'm assuming they're selling these, selling 4 cases per order. It is not enough just to say they're selling 4 cases because they're not selling 4 cases, right? This line tells me at the very end they've sold a lot more than 4 cases. We need that per order. So you could say they're selling 4 cases per order. You could say every order is an order of 4 cases of paper, something like that. But we need to mention the cases and the orders, both of those when we're describing the slope. So this is an example of what we're going to do for the others. I'm going to move my face again and have you look at number 2. Number 2 is the market value of a house is determined by the size of the house. Just like we did over here, go ahead and identify your slope and your y-intercept and see if you can put into words what those 2 numbers tell us about the situation about a house. Pause the video and do that now. Okay, so to start us off, I had started with the y-intercept, so we can start there as well. What did you get for your y-intercept? Well, our y-intercept is right here on our y-axis at the number 10. And what does that 10 mean? Did you say that our house starts at a value of $10? If you said $10, think about that. Does that make sense? Does a house cost $10? We all wish, right? That's why it's so important to read these labels. The label for our y-axis says it's the value in thousands of dollars. So that says that starting value is $10,000. And similar to what we did over here with our 60, what's that x coordinate? That's our 0. So think of it as like a starting value before you start adding on square feet to the house. So that starting value of the house, no square feet yet, just the starting value, is $10,000. So the Y-intercept would be the number 10 because that's what I see right here. But the interpretation would be that starting value of $10,000. I'm going to erase that 10,000 just because I want to make sure our Y-intercept label still says Y-intercept of 10. The other part of this we said was our slope. So I could come in. If we find our slope, I'm looking at that rise over run. So I see a point there. I also see a point here. My rise is 5 because I'm going from a 10 to a 5. I know I'm going up 2 boxes, but I'm going up 5 there. And then over, if I look here, it's at the line between 0 and 50. That would be 25. So I'm going up 5 and over 25. So if I simplify that, that's giving me 1 over 5. However, it goes back to this idea of that y-axis is thousands of dollars. So when I think about that 5 for my interpretation, I'm not going up $5, I'm going up $5,000. I'm going up $5,000 for every 25 square feet. So when I divide that out, it gives me 200, and that 200 is going to mean that your house value goes up $200 every square foot. So if your home has an area of 100 square feet and my home has an area of 101 square feet, that extra 1 square foot means my value goes up $200. Every square foot adds $200 of value to your home. And we can see, I keep talking about the value goes up because that line is going up, right? Which should make sense. Homes that are larger have a greater value. We'll do that same thing. I'm thinking let's choose one more for this video. Let's do number 4, which is about my tracking the amount of money in her savings account. So we've got this graph right here. Just like earlier, if you haven't tried one on your own yet, make sure you pause the video and try number 4. You're going to tell me what the slope is, the y-intercept is, and then what each of those things mean. Okay. So starting with that y-intercept, looking at our graph here, that y-intercept is this point right here. Now, I'm noticing that's not on like the grid lines, so I'm going to have to estimate. I'm going to have to make a smart guess. If I'm looking at that, I notice it's in between the line for 200 and this line below it, which is going to be 100. So if it's in the middle of 100 and 200, I'm going to estimate that it's about 150 there. Now, what does that 150 mean? Well, we're talking about my tracking the money in her savings account. That 150 is going to mean she starts with $150 in her savings account. No weeks have gone by. 0 weeks have gone by. So she's starting with $150. Lots of times I have students ask me, well, what's that written response going to look like? I would say that the Y-intercept represents that May is starting with $150 in her savings account. The second piece is going to be the slope, and that's going to tell us how that savings account is changing. So looking at our graph again, I need my slope. So I need 2 points on the graph where I can count my rise and run. Because this one is an estimate, I'm not going to use that one. I'm going to see if I can find a better point. I notice this point right here is nice and clear. And if I keep going up my line, this one here is good as well. So when I go to calculate that, I need my rise So my rise is going to be this change here. It might be tempting to count those boxes. I see 1, 2, 3, 4, 5, 6, 7 boxes. But notice that y-axis means I'm not going up $7. I'm starting at $600 and going up to $1,300. So 600 plus 700 gets me to 1,300. My rise is 700. My run is going to be how much I'm going over here. And again, it might be tempting to count those boxes, but if I come down here, I notice that we're not counting by ones. This is going to be 1 to 2, and then this is 2.5. So like, I guess halfway through the week. So from 1 to 2.5, that's going up 1.5 weeks. So my slope is 700 divided by 1.5. If I divide that out, I'm grabbing a calculator because I'm not sure if we're going to get an exact number. 700 divided by 1.5. I'm getting 466.66666 repeating. So 466.66 repeating, or you could say 466 and 2/3. I think because we're talking about money, which one is going to make more sense? This one, the one with the decimals, since we use decimals for money. And I might even change it to 466.67 and round that decimal. What does 466.67 mean? Well, it means that she is adding $466.67 each week to her bank account. So that would be that interpretation of the slope. I think this is a good stopping point for this video. Remember, our goals for this lesson were to talk about this relationship between graphs and equations. And you're noticing a theme throughout this entire thing is a lot of that relationship and being able to match them has to do with slope and y-intercept. We are going to talk about that more in our next lessons on connecting equations to graphs. But until then, I hope you have a wonderful rest of your day and thanks for watching. Bye.